Hello. This time we're going to explore the question of derangements and the principle of inclusion-exclusion. So we'll start with this question. How many arrangements of the word ABC are there that leave no character on its original position? Now, this time, this is an example that is small enough so that we can list all such arrangements and then start discarding a few things. So I'm going to create a small table where I list the permutation on one side and I indicate whatever the number of characters that are fixed in this permutation. So I have A, B, C. I'll just follow this lexicographical ordering. A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Now, then I count those that are fixed. So, well, I see A, B, C here. So 3 are fixed. They remain in the same original position. So now, in this one, I only see A. So I mark it as 1. Here I have B, A, and only C in the original position. So that is 1. For this one, well, B is not in the right position. C is not in the same original position. And the same happens with A. So this one is 0. Now, for the next one, I have C, A, B. And, well, none of the characters are in the original position, so I'll leave it with a 0 here, the number of ones that are fixed. And lastly, well, I have C is not in the original, B is in the original, but not A, so this counts as 1. Okay, so this time we resolved the problem by just listing everything. So we have 2 such arrangements where there are no characters on the original position. These ones are called derangements. But then we may continue and say, well, what if we want to find all the permutations of the word A, B, C, D, and, well, do the same thing, count the number of derangements. Well, that's possible, but there are 24 permutations of a 4-word letter. So that would be very inefficient. Why don't we try something else? Well, let's revisit the problem of derangements of a 3-word letter, as the one that we just have, and let's see what we obtain. Let's go back to the 3-letter problem. But now what we're going to do is try to understand it in a different way. Because the intention is to count the permutations that leave no element fixed, no character fixed. So I'm going to write it here. Permutations leaving no element or character fixed. Well, there's a different way of thinking of this, because what we can do is to present all permutations. Then from those, we're going to subtract the permutations that leave at least one character fixed. But then you say, well, but now you are over discounting. You have to put things back. Well, what is it I have to put back? I'll have to put back the permutations leaving or at least 2 fixed. But then once again, now we're putting too many things back. We need to remove a few things. And now we have to remove those permutations, leaving at least 3 characters fixed. So it's in this process of overcounting, discounting, overcounting, discounting. But now I think we have to stop here because, well, we can only remove 3 things, right? So that establishes the equality. Now, what remains for us is to actually perform the count on each of these terms. This one, this one, this one, and this one. Well, let's see what happens with the first. For this one, well, this is the same as saying permutations that leave at least 0 elements fixed. Well, that's fairly easy. What can we do? We can decompose this into a two-stage problem. One where we actually select the things that we want to fix, and then we permute. Okay, so how many you want to fix? Well, from 3 I want to fix none. And then I permute the elements that I have as a leftover. Well, there are 3 factorial ways of doing that. Now, for the next one, I'll follow the same scheme. Permutations that leave at least 1 fixed. Well, you fix, then permute. Well, now, from 3, we can choose 1, right, to do it. And we're left with 2 elements to permute, and we permute them. In this case, we're applying the multiplication principle, right, to perform these individual counts. Now, for the next one, same thing. I'll fix, then permute. You may say, well, that seems to be that you have to do it in that particular order. No, not necessarily, because I can first permute and then pick, as long as I do it carefully. So, from 3, I choose 2 to fix, and then I permute the one that is remaining. And lastly, well, same thing. I'll just write it for completion. I said fix, then permute. You would say, well, from 3, you choose 3 to fix, and then you're left with 0. You're left with 0 to actually permute. Well, there's only one way of doing this. Okay, well, out of this thing, well, we just perform the count. Subtract, add, subtract. And, well, this turns out to be, well, 1 times 6 minus 3 times 2 plus 3 times 1 minus 1 times 1, which, of course, is 2. The ones that we were expecting just from here. You may say, well, in what way is this more efficient than the thing that we just did by listing all the items here? Well, I have to agree with that, but now imagine that we expand the problem to solve this. How many arrangements of the four-letter word A, B, C, D, well, are there that leave no character fixed? Meaning on the original position. Well, I think this time it's much easier to count by following the scheme that we just provided here. How do we proceed? Well, we count our permutations, then we subtract those permutations that leave at least 1 character fixed, then we put back those permutations that leave at least 2 characters fixed, then we subtract those permutations that leave at least 3 characters fixed, and finally we add those permutations that leave, well, 4 characters fixed. So, but that's much easier, right? Now that we have the principle of inclusion-exclusion at our disposal. And we'll start with the count. Well, such permutations that we call derangements are just the following. They would be, from 4, you choose 0 to fix, and then you permute those 4. Then we subtract. From 4, you choose 1 to fix, then you permute the remaining 3. Well, now we have to put things back, right? From 4, we choose 2 to fix, then we permute 2. Then we subtract. From 4, we choose 3 to fix, then we permute 1. And lastly, from 4, we choose 4 to fix, and then we permute the remaining ones. Of course, now the count is much easier. This is nothing else but 1 times 24 minus 4 times 6 plus 6 times 2 minus 4 times 1 plus 1 times 1. Well, we'll do the actual count. This is 24 minus 24 plus 12 minus 4 plus 1, which results in 9. This is actually much easier than actually creating all the permutations of the four-letter word A, B, C, D, and then just eliminate the ones that we don't need. This is fairly more efficient. And it also has a plus in the following sense, that now we can solve even more complicated problems. Suppose that now we're given the following. We would say, I'll just state it. How many arrangements of a 5-letter word where all the characters are different leave exactly 2 letters fixed. Well, this is much easier than we may think. We just have to apply the multiplication principle. How? What we're going to do is just decompose this problem into 2 stages. Those stages are going to be independent of each other. And I'll just say this. As a first stage, I'll fix those 2 characters. And on the second stage, I derange 3. Well, this can be done in any order that we wish. As we can see, these are independent of each other. Well, let's follow the standard order that I'm providing here. Step 1, step 2. Well, let me explain it. What is that we're doing as we fix 2? Well, when we fix 2, what we're actually doing is from 5 letters that we have, we pick 2 to fix them. And we place them. Imagine that we're doing this as we progress. We have these 5 positions, 1, 2, 3, 4, 5. And the word in discussion is just an extension of the one that we have, A, B, C, D, E. And then we say, well, from the positions that we have here, we're going to select 2 that are going to be the ones that we use to fix a few things. Okay, so I'm going to fix this one and I'm going to fix that one. Well, and then I have to place the actual items. Well, this would be the second position. That's the one for the B. And then I'm going to place on the 4th position a D. Okay. Then on the next stage, what is I'm going to do? Well, from 3 characters, A, C, E, I'm going to pick 3 and derange. Well, how is that going to be achieved? Well, as long as I don't have a place, as long as I don't place an A, I'm okay. I'm going to place a C. Here, as long as I don't place a C, I'm okay, but I have to be careful. Well, here, I'm going to place, well, what can I do? Can I place an A? I can place an A, but if I place an A, then I'm forced to place the E here. No, I'm going to place an E here. And then I'm going to place an A here. There we go. Now we have our rearrangement. the one that we were expecting. Now, let's do the actual count associated with this. Here is saying from 5 you pick 2, and then you place them. Then from 3 you pick 3, and then you dearrange them. But now you're rearranging 3 elements. Well, we already know what that count is. That is 2. Okay, we're done. So, there are 5 choose 2 times 1 times 3 choose 3 times 2, which is nothing else but, well, 5 factorial divided by 3 factorial times 2 factorial times 2, which, well, actually simplifies to 5 factorial divided by 3 factorial, which is nothing else but 5 times 4, which is, well, 20. There we go. Fairly efficient way of counting. Take care. I'll see you next time.